In the early 1910s, most astronomers treated the universe as a finished thing. It had always been there, and it stayed the same on the largest scale. Stars sat in a broad system people called the Milky Way, and beyond that lay darkness that seemed endless but quiet. The big assumption was simple. The cosmos did not have a history. It just existed. Through telescopes, though, the sky refused to look tidy. Faint, cloudy patches appeared in many directions, and astronomers grouped them under one vague name, nebulae. Some were clearly clouds of gas inside the Milky Way. Others were different, small, smooth smudges that did not resolve into stars. Nobody knew if they were nearby objects or unimaginably distant ones. That uncertainty mattered. Because if the universe was truly static and eternal, those nebulae had to fit into a stable picture. Astronomers tried to catalogue them, compare their shapes and guess their distances, but their tools limited what could be proven. So the default belief held. The cosmos was steady, the Milky Way felt central, and the nebulae stayed as unanswered question marks scattered across space. In the 1910s, Einstein's new theory of gravity changed the rules. General relativity treated gravity not as a pull through space, but as the shape of space and time itself. And once space and time became part of the physics, the universe stopped being a simple stage. Matter told space-time how to curve. Curved space-time told matter how to move. That loop mattered. When scientists applied those equations to the entire universe, a problem appeared. A universe filled with matter meant gravity everywhere, and under that kind of gravity, nothing stayed balanced for long. If the cosmos started perfectly still, the math did not comfortably keep it there. It tended to shift. It tended to change. A static universe stopped looking like the natural outcome. That result forced a new question into cosmology. If the universe could not hold still, what did it do instead? It could spread out, or it could collapse in on itself. Either way, time became part of the story. The universe gained a history. Astronomers still wanted an eternal, unchanging cosmos, but Einstein's gravity pushed them toward motion. In the 1920s, a long-running argument finally started to break. Astronomers had called faint, fuzzy patches in the sky nebulae, but no one agreed on what they truly were. Then careful work led by Edwin Hubble showed that some of these patches sat far beyond the Milky Way. They were entire galaxies of their own. The universe instantly became much bigger than anyone had lived with before. Once those galaxies counted as separate worlds, their light carried a new kind of message. When astronomers spread that light into a spectrum, familiar lines appeared, like fingerprints, but they did not sit where they should. They shifted toward the red end. That red shift meant the light waves got stretched during the journey. Something had happened to the space between those galaxies and Earth, while the light travelled. The pattern sharpened into a rule. The farther a galaxy lay, the more its light shifted to red. Distance and redshift rose together. That relationship implied motion on a cosmic scale, not just in a few places, but across the whole map. Galaxies appeared to race away from one another. Space itself looked like it expanded. The idea of a fixed, unchanging universe started to collapse under its own measurements. By the late 1920s, the expanding universe stopped sounding like a simple fact and started sounding like a clue. If space had been stretching outward, then earlier it had been smaller, and if it had been smaller, matter and energy had been packed tighter. That meant higher temperatures and more violent conditions. Expansion did not just describe the universe's present, it pointed, step by step, toward a beginning. In 1927, Georges Lemaître pushed that logic further than most dared. He accepted the expansion and treated it like a timeline running backward. The farther back he went, the denser everything became, until the usual picture of scattered stars no longer worked. He proposed that the universe began as a single, extremely concentrated state. He called it a primeval atom. It was a start, not an eternity. Between 1927 and 1931, the idea gained a sharper edge. If the early universe had been that compressed, it also had been intensely hot, with energy and matter mixed in ways no telescope could directly show. That claim carried a consequence. The universe should still carry traces of that early heat, even after eons of expansion and cooling. The new question became simple and dangerous. What leftovers should still be out there? In the 1940s, a new kind of Big Bang thinking took shape. George Gamow, a bold theorist with a gift for big ideas, treated the early universe as a real physical place, hot, dense, and changing by the second. If everything once sat packed together, then the first question became simple and brutal. What happened to matter when the entire universe was an oven? Gamow and his collaborators, Ralph Alpha and Robert Herman, followed that heat forward in time. In their picture, the young universe expanded and cooled, and that cooling set the rules for what could form and when. As temperatures dropped, particles stopped smashing apart as easily. Stable nuclei could finally hold together. The Big Bang was not just a beginning, it was a timeline with checkpoints. Then they pushed the idea one step further, to a consequence that sounded almost too strange to test. If the early universe stayed filled with intense radiation, expansion would not destroy it. It would only stretch it out and cool it down. The light would fade, shift, and linger. So they predicted a leftover glow everywhere in space, chilled into microwaves, still filling the universe long after the fireball ended. In the 1950s, cosmology stopped feeling settled. The expanding universe still stood, but what that expansion meant no longer seemed obvious. A new idea stepped in and refused to treat expansion as a sign of a beginning. It claimed the universe stayed the same on the largest scales, not just from place to place, but from era to era. It was called the steady-state model. The steady-state picture said galaxies moved apart, yet the overall cosmos never grew old or ran down. For that to work, matter had to appear continuously in tiny amounts as space stretched, enough to make new stars and galaxies, so the average look of the universe never changed. It sounded radical, but it solved a psychological problem. It removed the need for a creation event. And it turned cosmology into a straight fight between two complete stories. Now the problem was simple and brutal. Both models could live with the same basic fact of expansion, so theory alone could not settle anything. The argument shifted to evidence and to a demand: find an observation that only one universe could produce. If the universe truly had a hot, dense youth, it should have left a trace behind. If it had always looked the same, that trace should not exist. Cosmology waited for a decisive test. By the early 1960s, the debate needed something solid. The leftover radiation predicted years earlier sounded almost too simple. If the universe began hot, then space itself should still carry a faint afterglow. The key shift came when a small group at Princeton, led by Robert Dicke, treated it not as a forgotten idea, but as a practical measurement problem. Dicke's team asked a straightforward question with big consequences. What would that ancient heat look like now? Expansion would have stretched the original light, pushing it down into microwaves far below visible sight. It would not come from one direction. It would come from everywhere at once, a nearly uniform background, like a constant temperature that no telescope could point away from. That realization changed the hunt. Instead of searching for rare events in distant galaxies, they prepared to listen for a weak, steady signal that filled the sky. They estimated it should be only a few degrees above absolute zero, so faint that ordinary sources of radio noise could easily drown it out. But the prediction also meant something else. The test was finally within reach. In 1964, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, worked with a large, horn-shaped antenna built for clean, sensitive measurements. They aimed to measure faint microwave radio signals with as little interference as possible. But almost immediately, their readings carried an extra background hiss. It stayed there, no matter where they pointed the antenna. It was weak, but it was stubborn, and it threatened to ruin the precision they needed. They treated it like any engineering problem. They checked the electronics, swapped components, and tested for faulty amplifiers. They looked for radio leakage from New York City, from passing aircraft, from the ground, even from the antenna itself warming and cooling. Every obvious source got questioned and ruled out. Still, the noise remained steady and smooth. It acted like a signal spread evenly across the sky, as if the universe itself produced a constant microwave glow. The most frustrating part was its uniformity. Real radio sources rose and fell as the antenna moved, but this extra hiss refused to budge. It did not depend on direction. It did not depend on season. It did not depend on time of day. Penzias and Wilson even chased down mundane contamination, including material inside the antenna that could add unwanted emission. Nothing made the effect disappear. By 1965, the noise stopped looking like a mistake and started looking like a clue. By 1965, the Bell Labs team still faced the same stubborn fact. No matter what they tried, the horn antenna kept picking up a steady extra signal. It did not come and go. It did not point to any one place in the sky. It behaved like a background. The problem was they had no good reason for it to exist, so they reached out, looking for anyone who might recognize it. That contact reached Princeton, where a group led by Robert Dickey had focused on a very specific expectation. If the universe once had been hotter and denser, space should still carry a faint microwave glow today. The numbers matched what Bell Labs measured. What looked like an annoying instrument error now lined up with a prediction. Two separate efforts suddenly clicked into one explanation. The result moved fast because the meaning was hard to miss. The Bell Labs signal fit relic radiation, cooled by billions of years of cosmic expansion, arriving equally from every direction. It was not just another data point. It was a test the universe had passed. When the finding was announced, the background noise became a message. The cosmos had begun in a hot early state, and traces of that heat still remained. The discovery settled the argument, but it did not finish the work. Scientists needed to know if that microwave hiss really matched what a hot early universe should have left behind. Decades later, Kobe measured the background spectrum in detail. It matched a near-perfect blackbody curve, the exact shape expected from heat that once filled all of space. The key point landed hard. This signal looked like cooled, leftover fire. Then came a sharper question. If this radiation came from the early universe, it could not be perfectly smooth. Tiny differences had to exist because structure needed seeds. WMAP mapped those faint variations across the whole sky, and the pattern appeared as minute temperature changes, only parts in 100,000. They were small, but they were everywhere, and they were coherent. The background stopped being just a proof. It became a measurement tool. Planck pushed the map to even finer detail and tighter precision. The anisotropes formed a rich fingerprint, and each feature narrowed what the early universe could have been like. The old assumption of a static, unchanging cosmos had already failed, but now the replacement stopped being a vague origin story. It turned into a tested timeline constrained by data. A faint microwave glow, once dismissed as noise, anchored a detailed Big Bang history.